Welcome to the lecture series on GPU programming and architecture. So, in the last lecture we have been discussing about how to query GPU device properties, and there is a good reason behind that you can write your program in a architecture oriented parameterized manner. So, that you can first run this kind of diagnostic code to figure out what are the different architectural parameters, and accordingly you can decide the launch parameters and some other parameters of your kernel, so that it executes optimally in a given architecture with respect to the execution time of the kernel. So, we were discussing some specific CUDA APIs for target GPU systems. For example, if I use this CUDA get device count function call, I get to know what is the number of devices in the system. I can use a CUDA device properties call to return different property values for a particular device. Now, just we will see some highlight of an example program. So, consider this scenario that you have a small host side code from which you are launching this CUDA get device count function call, and it would be returning the get device count in the variable that has been passed here, right, and then you are going to use this initialized variable. The variable gets initialized from this call. You are going to use it to upper bound the number of iterations for the succeeding loop, and then in using this loop, the first thing you do is you initialize a variable def p of type CUDA device property, and then for each index value I of this loop from I equal to 0 up to the device count, you are making queries per device, right. So, you are now calling the function CUDA get device properties, passing it a structure of type CUDA device prop, the name of it is def p here in this code, and passing it the device ID 0, device ID 1 up to the device count, the total number of devices we do go of course to the last device. So, in that way, for every device ID you have the corresponding device information getting stored in the CUDA in the structure def p of type CUDA device prop, and that again you are going to print using this specific function print device property, right. So, this is something which we have customized for our purpose, the print device property function. So, essentially it is being passed this device property structure, right. So, essentially in this case it is expecting that it would be given a CUDA device property type structure, and that it would be having several other fields which we will be printing through these printf statements. So, I am not going to discuss this printf statements in detail, does not make much sense. Rather than that, let us look at how the code, I mean what really the code will output, and of course, the slides will be with you, and you can have a look into how is essentially these different printf statements are organized. And so, overall if I run that code, these are the different device properties I can extract. So, I can actually extract the different revision numbers of the architecture. So, that is basically the device properties major and minor field. So, this major and minor field is telling me what is the major revision number and the minor revision number of the architecture, the name of the architecture family. So, that is the name of the device family, and then I have the total global memory size available for each device. So, for this device I have a total memory size like this, and then there are several other memory segments. For example, this is the total global memory, what is the amount of shared memory per block, what is the amount of registers per block, what is the warp size, maximum memory pitch, what is the maximum number of threads allowed per block, and for each of the block definitions, what is the maximum dimension of the block in each of the 3 possible dimensions, and finally lifting from blocks to grids, what is the allowed dimension of the grid in the 3 possible dimensions x, y and z. So, these are the possible values that get printed, and of course, the GPU's clock rate, the total amount of constant memory that is there, the texture memory, and whether the GPU supports certain other properties like concurrent execution of kernels, what are the total number of SMs in the GPU and all that. So, if we execute the earlier diagnostic code, these are the different messages that can get printed and they can be useful for framing your launch parameters of the kernel. Now, so that is about how you can extract the device properties. Now, since we are actually discussing about warps, scheduling the warps, there is another major issue which impedes the performance of a kernel, which is called control flow divergence. Till now, we have been just discussing that when you launch the kernel, you are essentially launching multiple thread blocks. Each of the thread blocks progress at its own speed. Inside the thread block, I have a collection of warps that are decided by the internal schedulers, and the warps will also proceed at their own speed. Since each of the SMs are able to execute a lot of warps together in parallel, it can tolerate the latencies of long latency operations, and in that way a GPU is able to make progress with lot of threads in parallel. The progress of each thread may be slow due to latency of operations, but overall the GPU would be giving you high throughput because it is completing a lot of operations in parallel. However, this question that how many operations really the GPU is executing in parallel depends on something very important, which is the flow of control inside the kernel. We have been assuming that threads can make progress in parallel inside a warp, but that really need not always be the case. For example, we know that by definition of a warp that the threads inside a warp execute the same instruction. At any point of time, they are executing from the programmer's point of view, they are executing the same instruction. What if there is a branch statement which the warp is executing, and some of the threads in the warp satisfy the condition of the branch, while some of the threads in the block do not satisfy the condition of the branch. The GPU is not capable of running both the if and else blocks at the same time. That is not how it is designed, that it will make progress with the warp or it will fork the warp into two parallel lines, so that some of the threads progress with the if part of the code and some of the threads in the same warp would progress with the else part of the code. Speaking, I mean, if you just think logically, that also does not make sense, because if you allow the hardware to fork a warp and still progress in parallel, there can be further subsequent forks, right. So, how will a hardware be able to handle so many number of forks of a warp and make it progress? Does not make sense in terms of implementation complexity, right. So, we are not getting into that detail right now, but rather we will try to understand how really a GPU handles such divergence of control flow that comes from branch executions. So, suppose you have a warp scheduler and it is executing these warps, and as long as the threads inside the warp are executing the same instruction, it is a very efficient situation. The problem comes, as we discussed, that threads inside a warp start executing different instructions. So, then the number of threads which are executing in parallel will reduce and we will have less amount of throughput, and that is a phenomenon which is known as warp or warp divergence, which leads to performance loss from the perspective of the GPU's throughput. So, as an example, let us consider a divergent code. So, this is a kernel where it is a very simple kernel. We are just labeling each of the statements in this kernel with labels P1, P2, P3, P4 and P5. There is a reason for that. So, the program statement with label P1 just computes the global thread ID for that specific kernel, for that specific thread in the kernel. The program statement with label P2 decides whether that thread will actually satisfy or not satisfy the if block. So, essentially all the thread IDs which are even would satisfy it, and they would get in to do the execution of the statement P3. The thread IDs which are odd indices would actually get in and execute the statement P4, and after that all the threads together would execute the statement P5. So, overall here we have the scenario that since the if condition is TID percentile 2, half of the threads of a warp would execute the addition instruction while the other half of the threads in the same warp would execute the subtraction instruction. And as we have decided, it is not the case that the warp would actually split and half of the instructions execute one instruction and half of the threads execute the other instruction in parallel. That is never going to happen in the GPU. So, how really does the hardware handle this scenario? So, the GPU does the following whenever such a branch comes. So, if we look at the corresponding PTX code for this kind of a kernel, we see that the PTX assembler maintains internal masks, or essentially the execution of all such instructions is what we call as predicated instructions. So, it maintains a mask as a bit pattern which would decide which instruction would really be executed, and the status of the instructions are actually stored in something called a branch synchronization stack. So, the PTX assembler sets the branch in synchronization marker first for the divergence statement, the if statement, and pushes a mask on the branch synchronization stack for each of the SIMD threads. It will decide that whether the mask value would actually decide which thread is executing or not executing. Depending on the value of this mask, the warp scheduler simply makes progress with the instructions, and once the instructions for the if block are finished, then the active mask is popped out from the stack and it is flopped. So, when it is getting flipped, essentially the mask changes. So, whichever were the 1 entries will now change to 0, and whichever were the earlier 0 entries would now get changed to 1. So, essentially the other instructions, the other thread IDs which were now stalled would now start executing. Essentially then once the if block finishes, the else block starts execution. Well, it is too verbose a description possibly. So, we would make it much more alive through a running example in this case. Just a brief summary in this case would be that when the corresponding assembly code is generated, a suitable marker is decided, right, and at the runtime when these predicated instructions with markers are getting processed, a separate data structure, a branch synchronization stack is set up, and which instruction would make progress and which instruction would not make progress is actually encoded as a 1-0 pattern and stored in the branch instruction stack. So, when the if block progresses, the threads corresponding to him, I have a 1 in that stack would make progress, and once the if block ends, I actually bring out this 1-0 pattern, flip it, and if I flip the pattern, now essentially then I have in terms of the hardware, it would know that whatever is corresponding to 1 in the pattern would actually be the threads in the else block, and now they would make progress. Let's look at it rigorously with a example here. So, this is what we call the control flow graph of the corresponding program we had earlier. So, we are making good use of the labels here. So, just have a relook into the different labels P1, P2, P3, P4 and P5 for the kernel. So, P1 is for the thread ID computation, P2 for if, P3 for the addition. Then after the else, I have the P4 for the subtraction operation, and finally, the common operation has got P5. So, here I have P1 followed by P2, the branch where that is the if condition, if TID %L2 is 0, and then I have a fork here to P3 or P4. So, some threads would go in here and some threads would go in here, and once this if condition ends, I have the thread synchronization together, and then I have all of them executing P5, that is this operation. So, I believe this actually should be star equal to 2 here, right. So, now let us try and find out that how the warp progresses with help of this kind of a branch synchronization stack and the predicated execution or the masks that we have been discussing earlier. So, this is how, let us say these are the threads which are going to execute for the kth warp, and they are right now in executing the instruction for the label P1, there they are computing, all of them computes the thread ID. Then all of them comes to the branch instruction. So, when all of them comes to the branch instruction, it will actually see that the branch condition is satisfied by the threads with even IDs, right. So, those who actually satisfy would be considered as a 1, and the thread IDs which do not satisfy are considered as 0, and this way active mask is created, the 1 0 pattern, and this initialized active mask is now stored into the branch synchronization stack. Essentially, the location of the ones would decide which threads make progress, and this is how the hardware takes care of making progress with the warp. It simply looks into the active mask. Accordingly, as we discussed, that these actually signify which of the predicated instructions would make progress. Since each of the even thread IDs are having 1, so those are the thread IDs that would make progress. As you can see that now I have half of the threads making progress, the TIDs which are even. So, they would all execute P3. Once that is done, once the execution of P3 is done, then these mask bits are complemented. So, P3 is done, I have complementation of mask bits. So, this pattern is going to change to the reverse pattern, which is this. With the reverse pattern, the hardware will again start executing the masked instructions following this mask. So, it would essentially use this sequence to compute which of the threads will make progress. Now, these are the alternate threads that are making progress. After this, all the threads are supposed to converge together and start executing together. So, that would mean from the branch synchronization stack, the mask is popped, and since there is nothing here, so the hardware warp scheduler would simply make progress with the entire warp, right. So, the question which is obvious here is, why do I at all need a stack kind of thing? Because here I was simply making progress with the warp. Since there was a branch instruction, I actually computed which are the threads that satisfied the branch. From a hardware implementation perspective, I represented that with a 1 0 bit pattern. Whichever has got 1, which TID was 1, corresponding to that I set some mask the predicated instructions as active, and I made them flow. Corresponding threads makes progress, and after those threads executed P3, I just in terms of the hardware I just reverse the bit pattern. So, then I could get the other thread IDs to make progress with the alternate flow of instructions or alternate flow of instructions which was in P4, and finally I just I actually reached the synchronization point. At that point I just set off the mask and I just made progress with all the threads, right. So, that is a simple thing. Consider the scenario where you have this kind of cascaded ifs, which is so common in a general program. How would you then handle it? For that is when I would actually require this kind of a branch synchronization stack. So, we consider this second example of a divergent code. Now, this is where we are actually considering nested if else statements, and we are trying to figure out how these nested if else statements would actually be handled by our divergence handling scheme in terms of that branch synchronization stack. So, just look into it very minutely. So, first we compute the TID. If the TID is even, we get into a branch. Inside this branch, we also check whether the even TIDs are divisible by 3. So, only those TIDs which are overall divisible by 6 would get into this part and do an addition by 3. Otherwise, the even TIDs which are not divisible by 3 would get into the else block and subtract 3. For all the odd TIDs, if they are divisible by 3, you have something. If they are not divisible by 3, you have something else, and finally everything converges to the location P9. So, this is like a more complex program. The complexity is just in terms of the nesting of if else statements. Have a relook into the original program. We had a single level of if elses. Now, here in this program, we are considering further nesting of if else statements. Look into the control flow graph here. So, you have positions P1 for TID computation, P2 for the first branch, P3 for the next branch, which is only satisfied for everything which is percentile 20 and also percentile 30. That means TIDs which are divisible by 6. then you execute P4, otherwise you execute P5. When this both are done, you execute P6, then you execute P7 and then P8. Finally, everything synchronizes and you go to P9, right. So, this is the structure of the control flow graph. Now, let us look into our original idea of warp execution. So, your warp starts, you initialize the active mask. So, at P2 you compute the mask, which is basically the sequence of 1 0 1 0 like that, because TID percentile 2 is 0. So, all the event thread IDs are satisfying the mask. So, you make progress here with all the event TIDs and you are here. And then what you do is, again, since you are facing a nested if. So, this is the situation which we are discussing, that you have already taken care of first if. Based on that if, you have pushed in a mask. Once inside the if part of the logic, you are facing the second if, right. So, for this second if, you have this condition. So, the first thing you do is you push the old mask into the stack. What is the old mask therefore? The old mask simply signifies what is your original thread of computation. The old mask signifies execution of the if part of the first nest, right. Now, you are actually going to come into the if part of the second nesting. So, how to do that? So, you have pushed the old mask once again and then you are applying this condition on the old mask. So, essentially you are trying to figure out which of the TIDs are going to progress and execute P4, right. So, figuring that out would mean applying this condition of the if on the old mask. So, and finding out which of the threads are really going to execute here. Now, as you can see from the conditions, only the threads which are divisible by 6 in terms of TID will execute P4, and that is what it is. So, this is the old mask and you apply the condition here. So, that would give you all zeros and only 1 at the 6th position of the TID, 0, 1, 2, 3, 4, 5, 6, only have 1 1. So, only this thread ID will proceed and execute P4, that is all is happening. After that, you are supposed to execute P5. How will that happen? So, all you need to do is you have to complement the relevant bits of this entry in the stack, right. So, you just complement the entries, because this was your old mask, this is your old mask, 2 instances, second instance because of the nesting. First, you apply your mask on the instance and figure out how to execute, who will execute the second if, and then you just reverse this pattern. With the reverse pattern, you execute the else inside the if. So, once this is done, so this is the progress of these 3 threads here. So, once this is done, you will just pop the stack. Why? Because this segment of P3, P4, P5 execution is done. So, you are essentially done with the if of the if part of the first level if. Now, you are going to process the else part of the first level if. How do you do that? Now, you are using the older logic. So, all you are going to do is you are going to complement the relevant bits. So, this was your original bit pattern of the old mask, you complement the relevant bits. Once you complement the relevant bits, you have the other half of the warps progressing to P6, where again you have another mask to execute. So, again follow the old algorithm, you push the old mask. So, again this is the old mask corresponding to the reverse pattern here, so that you are taking care of the other threads who are executing inside this else. So, for this old mask, again you will apply this condition TID percentile 3 is 0. So, if you apply this condition, you get only this thread which will execute here. Why? Because it has to be an odd thread ID 0, 1, 2, 3, but still it has to be percentile 3 equal to 0. So, it will only be made by thread ID 3, because the next thing that is thread percentile 3 is 0 is 6, which is not odd. So, it would definitely be a 0 here. So, you will have only one thread progressing, and then the rest of the threads need to progress with the else part. For that, again you have to complement this mask. So, this mask gets complemented and accordingly the hardware decides which other threads would progress. Once this is done, so you have got all the diverging threads reconverging back here in this NDIF, and that is signified by popping the stack. So after this there would be another synchronization. So first time you pop the stack to identify that okay, this sequence of second level ifs have converged, but then you figure that well, the first level if has also converged, right. So that is signified by popping the stack again. I hope this is clear. There were two pops. The first pop signifying that okay, this flow, let me mark the flows here. So the first pop signifies that this part of the flow has converged, and then you will pop the stack again and empty it, because that would signify that from the high level the entire flow has converged. The entire flow has converged. So you pop the stack completely. So overall this is the idea that in terms of the hardware and the PTX predicated instructions, how the GPU would really handle this diverging of warps and then reconverging back the threads in the warp. One important thing to notice here is that whenever a warp diverges, you have performance loss. Why? Because whenever the warp diverges, you have less number of threads executing per warp, because whenever I have a divergence, half of the threads, or not half, the threads which satisfy the if condition would progress, and then subsequently at some other point of time the thread satisfying the else condition would progress. So essentially I have the warp making progress with some of the threads executing which satisfied the if, and then at some point of time some other threads executing which satisfy the else. So whenever there is the divergence in your execution of a CUDA program, you have performance loss. So divergence is not a good behavior for your program, and there are a lot of research which go on in developing tools and techniques which identify whether your program can exhibit divergence, whether it may be possible to overcome it by an alternate program and things like that. But divergence is a serious issue which as a programmer you need to be aware of, so that you understand the way the program is going to behave in terms of architectural timing. In this lecture, we would like to summarize with some specific programming tips, that as a GPU programmer, you have to be architecture aware. That means you need to be aware of the hardware imposed instructions, or the hardware imposed restrictions in terms of how many threads can be mapped into an SM, how many blocks can be mapped into an SM, how many threads are allowed per block, and how many threads execute inside a warp, things like this, because these are the figures which actually help you to write a performance aware program. And something very important with respect to our earlier coverage of synchronization of threads would be this, as we have discussed that synchronization primitives of GPU programs work inside thread blocks, right. So suppose you are trying to synchronize or have collaborative execution among threads across multiple blocks, that is not allowed. So the only safe way to synchronize threads from different blocks would be to terminate the kernel right at that point. That would mean that all the computations get done at that point, and then you make a fresh launch of a kernel at that point, so that all the threads would get launched again with a consistent view of the memory. So with this we will be ending this lecture. Thank you.